Hello, all my quarantinis. My name is Joshua Evans, and this is part 2 of the Elctro-Magnito sense ring, and trying to make the wireless charger for it. And this is a bit of more of an update video, not really a demonstration, because I've been having trouble making this wireless charger. This is the very first time that I wanted to use MOSFETs instead of basic transistors to transmit large amounts of power. Every single other wireless charger I've ever made took so long to charge that it was almost impractical. The very first wireless charger I made, it worked. It just took literally 2 days to charge the device I wanted to charge. No way I'm doing this with this ring. This ring is going to be professional, or more professional. So I want to use a MOSFET. And a MOSFET allows for crazy amounts of current to go through a coil, generating a much stronger magnetic field. But I've been running into problems. When you hook up a coil directly to all that current, what happens is the MOSFET got hot. And not just like, ooh, that's hot, like, ow, my fingers melting off hot. Like, I can put my hand over it and feel the heat waves coming from it. And then it just shuts off. And I know I can't touch it because I can feel the heat. It's burning my hand and I'm not even touching it. So I got an eyedropper, and I put water in it and put it over the MOSFET. It evaporated literally in an instant. So it's over 200 degrees, over 212 degrees. It's probably, I have no idea how hot it was. I want to get an infrared camera so I can actually see, one of those thermal cameras, so I can actually see how hot it is without having to touch it. But it's extremely hot. I can't touch it. I'm doing something wrong. And I just went through MOSFET after MOSFET after MOSFET and just kept breaking it, and I couldn't figure out why in the world am I breaking it. And this is where the math actually becomes important. If you look at that equation, the one from my previous video, you should definitely watch that video. It shows that changing current creates, in a coil, changing current creates a voltage across it. And because it's a square wave, like this, the change in current isn't exactly going to be vertical, because then that would mean infinite slope. Not infinite, but like indeterminate slope. And that just doesn't exist in the real world. So there's a bit of a slant. But we can determine that it's actually quite huge because it's almost vertical. So the voltage generated will be immense. And I think I measured about 100 volts. And that 100 volts is going back into the MOSFET and destroying it and getting it crazy hot and then just making it useless. So I needed a way to somehow dissipate that energy before it goes back into the MOSFET and destroying it. And there's a perfect solution for that. It's called a flyback or a flywheel diode. And what that does is it gets that 100 volts, gives it a channel to go, and it shorts it with itself through the diode. And what that does is transfers that 100 volts into heat. And it shouldn't be that much heat. It shouldn't be that much heat. Not really. But it was. This thing started to burn as well. The MOSFET was perfectly safe. The diode started to burn. And I'm like, what is going on? So I tried a bunch of other solutions. I tried a thing called an H-bridge and using a hex inverter to create two signals. One that is offset with the other by 180 degrees, meaning when one is off, the other one's on. So it flip-flops like this. And then you set up 4 MOSFETs to allow, instead of just turning on and off the current this way, you allow it to do this, flow back and forth like this. And then you could put a capacitor, or a device that is the exact opposite of an inductor, in which if it's DC, if it plateaus, a voltage is generated. And if it's changing, if it's a changing current, there's no voltage, so it shorts it out. And that's what I wanted to make. I could put that in series with the inductor and allow it so that when it's plateaued like this, when it's just on and drawing heat, it doesn't stay on. It doesn't go into the inductor and cause it to get really hot. That didn't work because my hex inverter only takes about 3 volts, but my power supply is 12. I'm definitely using 12. So, when I stepped it down to the 3 volts that was needed, it wasn't even able to do anything. So, scratch that. I use a thing called an operational amplifier, which I can do the same thing, invert it. That didn't work. I tried even transistors, just basic transistors, and that didn't work. So what in the world was going on? I started looking deeper into these diodes, and the diode I was using has a very low switching frequency. I'm switching this thing on and off about like 30,000 times every single second. Greater than that. Greater than 30,000 times per second. And this diode wasn't able to keep up with that and started creating I don't really understand exactly what happens, but it creates like a secondary voltage, and that competes with the primary voltage and it just becomes ineffective at really high frequencies and starts to heat up. So the diode you're supposed to use is a thing called a Shakti diode, which is for high frequency applications, like this one. But when I plugged it in, it exploded. Why did it explode? Well, they can only take 3 volts, so I even tried putting them together. It still didn't work. And then I looked back at the formula. How in the world can I get this to work? V equals inductance times the derivative of current over time. And what was happening with the graph? When you put a square wave, because that's what I'm sending into it, a square wave that looks like this is almost vertical. So there's tons of voltage there. But because the energy is being taken away, that's not the problem. When it does this, the energy goes into the magnetic field, so I don't really have to worry about dissipating that energy. It's on the downtick. It's when it goes down is the problem. All that energy that was in the magnetic field gets dumped back into the system and causes stuff to overheat and reach 100 volts and stuff. But then I looked at it. If I can somehow change the slope or the average slope of the downtick, I can decrease the voltage across that diode. And what if instead of getting a signal that looks like this, right, with this slope being crazy, not low but negative, right, we make it more like this. So it's like this, or this more realistically. It'll look like this, right? If we can get it to look something like this, the highest, it's not really changing that much current compared to just a straight line like this. It's more slanted like that. If I can get that, the voltage would go down substantially. But what would allow me to do that? Then it hit me. A capacitor hooked up to ground, because a capacitor actually stores energy. So on that first thing, it uses some of that energy to charge up the capacitor. And then once it turns off, that voltage that is stored in the electric field of the capacitor turns back into normal electrical energy and slowly dissipates it. Or does it look like, yeah, it looks like this. And I hooked it up to the input of the MOSFET, and sure enough, nothing got hot. Well, things didn't get as hot. I think I need to tweak the values a bit more so that I can maximize the magnetic field, right? Because if you do this capacitor too much, what happens is it's going to be like this, and then the next one will be like that. And then you just get these things, meaning it's constantly on, meaning the change in the current will be less than what I want it to be, ruining the efficiency. But if I can just get it to the slight point, so when this reaches a minimum point, then that is when it goes back up. So I need it to be like that. Now adjust the values and all that stuff. And once I get that down and re-hook up all the detection, the current detection stuff, then we can begin on the near field communication and the actual charging portion of this, and make the circuit for this thing right here, and finalizing the wireless charger. So yeah, look forward to that in the next video. But this has been Joshua Evans, and have a great quarantine break, and stay safe and all that stuff. So see ya.